Okay, grade 12 chemistry. This is the second lesson in organic chemistry, and we're going to bring in a lot of new stuff today, including the concept of priority and doing some organic reactions. So this one is not to be missed. Here's what we're talking about today. We're doing alkenes and an introduction to priority. We'll talk about some cis versus trans isomers. Then we're going to get into our first reaction, which is addition reactions for alkenes. We'll briefly segue over to aromatic compounds because they're cool, and then we'll do alcohol naming and elimination reactions, which is something that happens with alcohols and alkyl halides. All right, it's a long, it's a lot of slides, so I'm going to be talking fairly quickly. Let's get started with alkenes and alkynes. Alkenes is what we call molecules that have double bonds in them. And alkynes are molecules with triple bonds in them. And these are very interesting. Double bonds and triple bonds are more interesting than alkanes. The reason that they're interesting, there's a lot of electrons in one place on a double bond or a triple bond, and so other molecules can come in and install themselves on that double bond, triple bond. We've got open space for new molecules. So you can do some interesting reactions with it. Because they're more interesting, because we can do more reactions with them, they take priority in naming. We want people to know that there's a double bond on our molecule, and so we give it the priority. So this is the concept of priority. There is a well-defined priority list in organic chemistry, and different groups, different functional groups, take more or less priority. Here is an excellent picture of a priority list. You can see here alkanes, alkynes, and alkenes are pretty low down the totem pole. But there's stuff below them. Below everything below alkane just ends in alkane. And then we've got other more interesting things. The number one thing in priority is a carboxylic acid. We really like carboxylic acids in organic chemistry. It goes on down with different groups. Alcohols are here. We're going to talk about alcohols today. They're actually a fairly high priority group above alkenes. And interestingly, this is kind of odd, alkenes are above alkynes in priority. So, kind of neat. I do love this picture. It's a great picture. You can find it on Edsby. So what that means is it's got priority, which means that the main carbon chain, that longest carbon chain, has to have the double bond or the triple bond. If that's the most interesting thing, which it is on this molecule, it has to be part of the main chain. So we need these two carbons in our main chain. We need them there. Which means that when we decide what our main chain is, we have to use that. So this is not the main chain anymore, this whole long thing. Even though it's longer, even though it's got more carbons, it is not the main chain. The main chain has to have this alcohol in it. So there's our main chain. There's our actual main chain. They also take priority in naming. And numbering. So the numbering has to have the lowest number be on the alkene rather than going any other way. So even if there's a lower number somewhere else that you can do, this has to have the lowest number because it has priority. So that's the concept of priority. So we'd number this 1, 2, 3, 4, 5, 6, 7, and then this guy here just becomes a substituent. That just becomes a propyl hanging off of 2. So this becomes then, let me just change some stuff. This is a 2-propyl, right? 2-propyl because there's 3 carbons there, 1, 2, 3, and this is 1, 2, 3, 4, 5, 6, 7. So 7 hept. And then now we have to show that it has a double bond, not a single bond. And they're called alkenes. You can imagine it's going to have an ending that reflects that. This is hept 1-ene. 2-propyl hept 1-ene. The 1 refers to the location of the double bond. It's on 1. And the ene tells us it's a double bond. An alternative name for this is 2-propyl 1-heptene. That's also acceptable. So both are acceptable as names for this molecule according to IUPAC. You can go either way. So that's the concept of priority, and that's how you name an alkene. This is just kind of generally saying exactly what I just said. Yeah, so they take number priority and they take naming priority. We have to do it that way. One other thing to watch out for is cis and trans isomerism. This is the first time we're going to see R groups. R just means the rest of the molecule. It means another carbon chain somewhere. It could have other stuff on it. It just, other stuff. Things that aren't hydrogen. Something that's organic going off this way and something that's organic going off this way. This is a cis isomer. This is a trans isomer. The problem here is that single bonds, they can rotate. Single bonds can rotate. But double bonds are locked. They're locked together. They can't rotate. The reason for that is due to something called hybridization and pi bonding. Pi like the mathematical thing pi, or the Greek letter pi. So if you want to look that up, you can look at a pi bond and understand why they don't twist. But just know that they don't twist. So they can't twist. They're stuck. They're prevented from twisting. So if the two substituents are going down like this, like in the cis isomer there, and they can't twist, they're not going to change. And if we have the two of them pointing opposite directions and they can't twist, that's also a different structure. They're going to have different properties from having that structure. So this is the cis isomer, this is the trans isomer. Cis means same side, trans means opposite side. You might also run into E and Z. I'm not going to cover E and Z. You can look that up yourself. Yeah, triple bonds can't do it because triple bonds just have one on each side, right? Three, which only one on each side there, and they're linear. So triple bonds don't do cis and trans. And then certain molecules, like the ones diagrammed here, aren't cis or trans, right? It's not like all double bonds are cis or trans. These ones don't have a clear cis or trans. This is just two hydrogens here. So there's no clear cis or trans. This one doesn't have a cis or trans. And this one doesn't have a cis or trans. It's got two different substituents on this side, but two of the same on this side. So only ones where they're different can be cis or trans. So if it was something like, if this one had an extra, if it was like that, this would then become a cis alkene, because the longest carbon chain makes like a C like that. That's another way to think about it, C for cis. But that is not cis or trans. We can't assign a cis or trans nature to it. Yeah, so that's alkenes and priority. We're going to get into our first reaction. So I'm going to pause. So this is our first organic reaction. We call it addition. It's an addition reaction. This is a specific subtype of addition called hydrogenation, which is hydrogen, right? Like hydrogen. We're adding hydrogen to something. Addition of hydrogen. The reason that it's called addition is that we're literally adding the hydrogen. The molecule, this was C2H4, now it's C3H6, now it's C3H8. We've literally added the hydrogen in the molecule. There's no byproduct. We're adding it. In order to do this, it has to be unsaturated. Look at the keep in mind, right? It has to be an unsaturated compound because we want there to be space to add our hydrogen. If it was saturated, then we'd have to kick something out to add something else. So here's propene, add a hydrogen, you get propane. Propyne, a triple bond, if you had two hydrogens, you'll get propane. So, it happens for alkynes as well as alkenes. If you have something like cyclohexyl-1,3-diene, you can do the same thing, and then you're just adding hydrogens across all of the double bonds. You can think of it as breaking up the second part of the double bond, and now you've got two open spots for the two hydrogens that you're adding across the double bond. And each double bond is between two carbons. You're adding hydrogens across those two carbons. It's not super useful, not like a super useful thing, but it is used in stuff like making margarine out of vegetable oil, things like that. There's a cool catalyst here. You see the catalyst. The catalyst is a nickel or a platinum surface, and literally that's because the metal has these pits in it, and the pits are just the right distance apart for the hydrogens to sit. And then the hydrogens are right in line with the carbons for the double bond, and they can attach on across the double bond. A very cool example of a catalyst. We'll talk more about catalysts in Unit 3, thermochemistry, but this is a neat example of one, a little preview for you. Yes, that's addition. The basic kind of scheme for addition is that you have a double bond or a triple bond, and you're sticking your substituents on either side, on the carbons on either side of the double bond or triple bond, and usually heat will help. Here's a useful addition. It's adding a halogen to a hydrocarbon. This is halogenation. There are specific subtypes, so like fluorination, bromination. Here's a chlorination of an ethene. So this is ethene. We add chlorine to it, and it kind of happens by itself because chlorine really likes electrons. Right? It's an electronegative compound, so the chlorine will just break up the double bond on its own and install on either side. Remember, either side. We take the double bond, we break it, and now there's a space on either side for a chlorine. So this is ethene. It turns into 1,2-dichloroethane. Right, either side of the former double bond. So that's a different kind of addition. You can see why it's called an addition. It's still just adding the chlorines, but it's got this other subtype called halogenation. It works for alkanes as well. You can add like a bromine to it. The catalyst here is ultraviolet light because ultraviolet light will excite the electrons and make them easier for the bromine to kind of come in and steal. But there's no open space here. You can't break a double bond and make new room. You have to kick out a hydrogen. So what happens is you kick out one hydrogen, and one of the bromines will come in and replace that hydrogen. This is called a substitution reaction. It's a different scheme, right? Because you have a byproduct. There's a byproduct of HBr. So that's the hydrogen that you kicked out plus the other bromine that was left over from the Br2. That's how you can make an alkyl halide. So kind of a quick summary of that is if you have an alkane with a halogen, you get a monosubstituted alkyl halide. You get an alkene and a halogen, you get a disubstituted alkyl halide, disubstituted. And the halides are right next to each other because they just go where the double bond used to be. Okay, now into a really fun part. Well, actually, let's explain some schemes here. Why do we halogenate? Well, it's the first step to adding other compounds because for bromine, for example, other things can come in and kick out the bromine now. So you can take a butane, turn it into a bromobutane, then you can kick out the bromobutane and maybe install a double bond there, and double bonds can do cool stuff. Or you can install something else like an azide, and now you can do a bunch of different reactions. So yeah, so alkyl halides are really good starting materials. Yeah, that's a little practical practical chemistry for you. Now, naming them, we've talked about naming them. Alkyl is alkanes, alkenal is alkenes, alkynyl is alkynes. And then there's this concept of primary, secondary, and tertiary. Primary is right on the end. Secondary, there's 2 carbons attached to the carbon that it's attached to. And tertiary, there's 3 carbons attached to the carbon that it's attached to. This is the fun one. Here we go. This is the one I've been waiting for. Hydrohalogenation. So we've talked about Br2. If it was Br2, it would just go across the thing. But then what if we do HBr? The hydrogen's going to go one place. The bromine's going to go a different place. And it turns out that it has a preferred one to do, a major product and a minor product. The major product is the bromine going to the middle. Right? See the bromine's on the middle now. The minor product is the bromine going to the end. So we have to predict this, and the rule is called Markovnikov's rule. So I'm going to change my current topic just to say Markovnikov's rule. Markovnikov's rule. Markovnikov's rule. So Markovnikov's rule, here's what Markovnikov's rule actually says. And there's a picture of Markovnikov there. His rule basically says that the hydrogen will attach to the carbon that had more hydrogens to start. Right? So the way I like to say it is that hydrogen goes with its buddies. Hydrogen goes with its buddies. So maybe I will fix my keep in mind. Hydrogen goes with its buddies Right? Hydrogen goes with its buddos. Buddos, I like that. Buddies. There we go. Hydrogen goes with its buddies. Let's look at that. Let's look at this reaction in that context. We have this alkene. This carbon has one hydrogen. This carbon has two. The hydrogen is going to go where there's more hydrogens. So the hydrogen part of things is going to join there and leaves the chlorine to join there. So you get a major product and a minor product. The major product has the chlorine here. Minor product has the chlorine on the end. For this one, same idea. This carbon is full. So, 4 bonds, so no hydrogens there. There's 2 hydrogens here. 2 hydrogens here. So the hydrogen is going to go with the hydrogens, and the chlorine is going to go over here. And so that's what we expect. And then this one, same thing. This one's full. This one's just got 1 hydrogen. So the hydrogen is going to go. The hydrogen is going to go to that carbon, and the chlorine has to go to that carbon. Remember that they add across the double bond. So here it's going to look like that. This hydrogen goes here, and the chlorine goes here. So that's Markovnikov's rule for halohydrogenation, but also for other things. One of those other things is hydration. Hydration reaction means adding water, right? You add water, hydrate. When you hydrate, you add water to yourself. Same thing here. We're adding water across a double bond. It's easier to think of this water as HOH, right? There's a hydrogen and a hydroxide, HOH. And we're adding it across a double bond. Same thing. The hydrogen is going to go one way, the OH is going to go another way. And this follows Markovnikov's rule. Split the water into an H and an OH. So that might be a good place to start. H and OH. I like to think of water as HOH. And the hydrogens, here's the double bond that we're going to add across. One thing's going to go to this carbon, one thing's going to go to this carbon, right? Which way is the hydrogen going to go, the single hydrogen? Well, it's going to go where there's more hydrogens, and that happens to be here. There's one hydrogen that's attached here because there's 3 bonds being made by the carbons. There's one left. No hydrogens here, so this hydrogen is going to go ahead and join the other hydrogen, leaving the OH to join on this side. So that's Markovnikov's rule. After this goes through this reaction, that double bond is going to be gone, and we're going to see, can't draw pentagons. I can draw hexagons really well, but I can't draw pentagons. Here we go. That's a pretty good pentagon. There's 2 carbons there. And the major product is going to have the hydrogen here and the OH here. Note that the double bond is gone. It used to be here, but now it's gone. And the minor product is going to be similar, except now the OH is going to be on this side. OH. Yeah. And the H would have gone over here. Right, so this is the major, and that's the minor. So this is major. Right, major product. So yeah, that's Markovnikov's rule. You have to remember that hydrogen goes with its buddies, and OH goes to the other carbon where the double bond used to be. That is Markovnikov addition. So this is also an addition reaction. Yeah, so a bunch of addition reactions. Right. Next up is aromatics. We're going to talk about aromatics. Aromatic compounds. So aromatic compounds are generally compounds that contain this structure called benzene, C6H6. We knew it existed as far back as 1825, but it took 40 years to figure out the structure because it was just this really weird structure. Here's a few of the weird concepts people had until eventually Kekulé worked it out. And it worked out to be 3 double bonds in a hexagon with this repeating pattern of double bond, single bond, double bond, single bond, double bond, single bond. But further research showed that the bond lengths are all the same length. So that shouldn't happen. Double bonds are typically shorter than single bonds. And this is where resonance comes in, right? It flips back and forth between these two structures. And so the concept is that it has this delocalized electron system. The electrons are actually wandering all around the ring. If you have a bunch of benzenes in a row, you can have electrons move through the entire compound, almost like a metal. You might have heard of graphene. That is how graphene works. It's got a delocalized system, kind of like a metal. Same with carbon nanotubes and things like that. They're made with these benzene structures. One thing to note, some other structures can be aromatic. So for example, here's a few different ones like furan, indole, tropylium, cyclopentadienyl. A few interesting different ones. There's also the one behind my face, which is pyridine. This is not aromatic though. Kind of neat, doesn't have that overlap. So you don't need to know that, but it's just kind of cool to know. What you do need to know is how to name these things. So here's a few different compounds that have benzene in them, and we're going to learn how to name kind of some of them. So here's aspirin, has benzene in it. Here's methamphetamine, has benzene in it. Here's I think morphine or something like that, has benzene in it. Or cocaine. That's cocaine, I think. Here's the testosterone, has a benzene ring. Tetrahydrocannabinol, you've probably heard of that one. THC, the active ingredient in marijuana, has benzene ring. Like that, there it is, benzene ring. They can be harmful, they can cause cancer. You might have heard of bisphenol A. That's bisphenol A. It's got benzene rings. But let's talk about naming. If the benzene is the main chain, for example here, there's 2 chlorines on a benzene. This is just called a 1,2-dichlorobenzene. We give benzene its own special name because it's got that special structure. And on the other side, we've got 1-ethyl-4-methylbenzene. Again, benzene as the main structure. And we number them, for lowest numbers. This is 1,2 because it's 1,2. This is 1,4 because alphabetical order. Ethyl comes before methyl. So you should know that. There's one exception, benzene alcohol. If there's an OH on a benzene, it's called phenol. That's why this is called bisphenol. Phenol. But sometimes it's easier to stick the benzene as a substituent. As a substituent group here. Basically here we want the double bond as part of our main chain. So it's easier to name the benzene as a side chain. We call it a phenyl group. So this is 4-phenyl. Phenyl is this big benzene ring attached, right? Attached to number 4, pent-1-ene. Pent-1-ene. Because 1, the double bond is on 1. 1, 2, 3, 4, 5. That's pentene, pent-1-ene, and then the benzene is the substituent. That's phenyl. So phenyl refers to a benzene group. And one thing about the aromatics, that resonance structure is very strong, that ring. So it doesn't want to break the double bond. So when we try to do like an addition for it, it's not going to go. It's not going to add, it's just going to substitute. All right, we try to put chlorine on it. It doesn't put the chlorines across double bonds. It just sticks it on the side where a hydrogen used to be, because there's a hydrogen sticking out of each of these carbons. It replaces that hydrogen with a chlorine. Okay? They do substitution reactions like an alkane. They're alkenes, because it's benzene, but it won't do an addition reaction. That's something to know. Also generally insoluble, but if you add different groups, you can change that. Put a lot of chlorines on it or something, you can make it more soluble, or OH groups in particular. Phenol, I think, is somewhat soluble. Yeah. And now we're going to get into alcohols, so I'm going to change my subtitles and stuff. A quick callback for alcohols, back to hydration reactions, which are a form of addition reaction because there's no byproduct. We're just adding the water straight to the alkene. We make it by adding H2O with a catalyst, usually a weak acid. They follow Markovnikov's rule. We get a major and a minor product. let's talk about naming these things. So alcohols have the highest priority we've seen so far, which means that the main chain must have the alcohol and the numbering must be lowest near the alcohol. And alcohol ends in -al, so the name is going to end in -al. But this is a kind of an important point, is we keep the an for ane, right? This is telling us that it's single bonds and then an alcohol. So here's ethanol, propan 1-ol. See where the number goes? It's 1-ol because you can have propan 2-ol, right? You have propan 1-ol and propan 2-ol. So the 1 says that alcohol's on 1. This 2 says the alcohol's on 2. Here's butan 2-ol, here's pentan 3-ol, and so on and so forth. Here's 2-methyl-propan 1-ol, 2-methyl-propan 1-ol, stuff like that. You can have tertiary alcohols as well, so 2-methyl-propan 2-ol, or 2-methyl-butan 2-ol. This is called a primary alcohol because the alcohol's on the end. This is a secondary alcohol because the alcohol is, there's 2 carbons attached. There's a hydrogen on the opposite side. This is a tertiary. The alcohol is attached to a carbon, and that carbon is just surrounded by carbons. So primary, secondary, and tertiary alcohols, which maybe I should put up. These are primary. These ones are secondary, including the cyclohexane 1,4-diol and the 3-hexenol. And this one is tertiary alcohols. When there's two alcohols on the same compound, you get a diol. And the same thing with the numbers, right? An 1,4-diol. And this one here is 3-hexenol. So you can add the ene. Sometimes the e here is taken away as well. Let's talk about numbering here. This is 3-hexenol. That's because alcohol takes priority, so the ol automatically becomes number 1. So all we need is that 3 to show that this double bond is on 3. 1, 2, 3. So it's 3-hexenol. Yeah, so that's alcohol naming. You can also name these. There's a different way that also is accepted. This is sometimes called 1-propanol instead of propan 1-ol. That sometimes works, and this is 2-propanol. Panol. That's an accepted name for these compounds as well. And this would be 2-butanol and 3-pentanol and stuff like that. But putting the number between the an and the ol takes away absolutely all ambiguity, that the number is absolutely linked to the alcohol rather than anything else. Here 3-hexenol. It might be maybe ambiguous whether the 3 refers to the hexene or the ene or the ol, but if you write hexene, hex 3 ene 1 ol kind of thing, then you've taken away all the ambiguity kind of thing. So that's naming alcohols. That's how you name them, and they have the highest priority we've seen so far, which means you can get into some interesting priority issues. I'm going to draw a molecule here. Let's draw a molecule like this. I'm going to put the alcohol here, right? And I'll put an alkene here. And if we want to name this molecule, let's throw some other stuff on here. Let's toss a chlorine here, and maybe we'll put a methyl group over here. Why not? When we name this thing has to take priority. This alcohol has to take priority. It is our most interesting, most important side chain, or most important group, because we're going to name this as an ol. We're going to name the ending of it is going to be ol because there's an alcohol here, which means the carbon chain has to be numbered to give this alcohol the lowest number, right? No matter what, this alcohol gets the lowest number. So even though this would give us a number 1 for this ene, we're going to go the other way because we want the alcohol to have the lowest number. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be a 4-ol. 4-ol is a non-ene for all. Actually, we have to say where the ene is, don't we? So it's not a non-ene for all. It's a non-8-ene. It's a non-8-ene for all. This is getting kind of complicated kind of quick, huh? This is about as bad as it can get for numbering, though, so don't worry too much. We're not going to get... It's not going to get much worse than this. We have to put our methyl group on 5 and our chloro group on 7. C comes before M, so chloro will come before methyl. So this is going to be 7 chloro, 5 methyl, non-8-ene for all. Yeah, so that's a kind of an overview of alcohol naming and priority. And if it was cis or trans, we'd actually have to say if it was cis or trans. But this one isn't. It doesn't have a cis or trans. There's no preferred orientation here at the end of the chemical. Let's actually add one here. Let's add another carbon going down. If we add a carbon going down, that's now trans, and it's a 10th carbon. So this would be now a dec 8-ene for all, and it's trans. The cis and trans comes all the way at the start, and it's actually separated from the full name. So this would be trans 7 chloro 5 methyl dec 8-ene for all. That's a heck of a molecule. So that's alcohol naming. We're gonna quickly jump over to the properties of alcohols. Here's properties of alcohols. It's got hydrogen bonding, so if you remember, hydrogen bonding is this very strong dipole interaction. So even methanol is a liquid. It's got a very strong interaction. The polarity means that they're more soluble in water than the alkanes are, so methanol, ethanol, and propanol, the small alcohols, are all miscible in water, which means you can, any proportion, you can have 70% alcohol, you can have 20% alcohol, you can have 2% alcohol, it doesn't matter. Past that, it gets a lot less soluble very, very quickly, just by sheer size. And they typically make good solvents, especially isopropanol or 2-propanol, a very good solvent. That's rubbing alcohol. You might have used it to clean, permanent marker off of something. Now we're going to get into the alcohol reaction called dehydration, so we are going to pause. Dehydration reactions are our first class of elimination reactions, which is a really cool name. We're eliminating something. So hydration reactions was an alkene plus water makes an alcohol. A dehydration reaction is going to do the exact opposite. An alcohol take away water is going to make an alkene. Or maybe a better way to say this is an alcohol will become an alkene plus water. Plus water, should be a plus. Here we go, plus water. So that's a dehydration reaction. And that's where that comes, dehydration, which is an elimination reaction. We're actually just ripping the water off of the molecule and installing a double bond like that. The catalyst here is sulfuric acid, typically, and a little bit of heat. Or phosphoric acid is also used often. This is sulfuric acid, H2SO4, because it really likes to pull water away from things. Other strong acids don't work. They'll usually end up leaving, like if you use HCl, it'll leave a chlorine behind, and that chlorine will attack your molecule. So we have to use something that has a bad nucleophile, which is a concept that you'll learn in university chemistry, I guess. So that's an elimination reaction. We're eliminating the water. We're pulling it right away, and we're installing a double bond. We have to eliminate from the 2 carbons next to each other. So if we look at this guy, we take the OH off of one thing, we have to take something else off of the other. I'm going to give myself some room by moving my face over to the corner. The thing that we're eliminating on the other side is the hydrogen. One of the hydrogens on this side, those two together are going to make the water, right? This hydrogen and this oxygen are going to leave and make the water, right? They're going to make the water. leaving behind the gap, leaving behind an empty kind of space, and that's where the double bond is going to be created. So yeah, that's an elimination reaction. And there's this rule for elimination reaction, which is kind of like Markovnikov's rule, but it's made by a guy named Zaitsev. It's kind of the opposite, though. It says that in an elimination reaction, the more highly substituted alkene will form. By highly substituted, we mean more carbons. So here's an example of it. Here's 2-methyl cyclohexanol. So 2 because 1, 2, right, going this way. All automatically gets the number 1. This is actually a bad name because of the capital letters. Don't use capital letters. IUPAC says it's bad. So here is 2-methyl cyclohexanol. We have to eliminate, and we have 2 options, right? We can pull. We know we're going to pull away this water. We know we're going to pull away a water from this thing because we're eliminating with phosphoric acid, and this OH is going to leave. So we know that's going to leave. It's a dehydration reaction. We're going to get rid of that water. But we have 2 options for which hydrogen to choose. Right? There's a hydrogen here and there's a hydrogen here. Hydrogen here and a hydrogen here. Which hydrogen is actually going to go with this OH? Well, you can almost think of it like hydrogen likes to stay with his buddies. There's actually 2 hydrogens here. Yeah, there's 2 hydrogens there because carbon makes 4 bonds. 2 hydrogens. There's only 1 hydrogen here, so it's actually going to prefer to rip away that hydrogen and install a double bond there, right? Because we have to take away that hydrogen. So this is going to be our major product. 84% of the time it's going to make this. 16% of the time it's going to make the other one, the minor product. So that is the elimination. This doesn't have to be for dehydration. It also works for something like a dehydrohalogenation. You can do that with a strong base and clean it up with HCl. So here's a chlorine, right? We know we're going to get rid of this chlorine. That chlorine's going to go away. That chlorine's going to go away. But in order to do that, we have to pull a hydrogen away from either this carbon or this carbon. Or even potentially this carbon, right? One of these 3 carbons is going to go. So we can install our double bond here, here, or here. And the more substituted one is favored. This one's going to have more carbons to it, or it has fewer hydrogens. And that's where we're going to form our double bond. We're going to form our double bond there. That's the double bond we're going to choose. So I'm just going to erase these so that it's easier to see, right? That's going to leave. That hydrogen's one of the hydrogens is going to leave. We're going to create this as our major product. So that's the more stable compound. That's the one that we're going to make. And this is the less stable compound, 30%. There's also a rule for cis and trans, and that one's pretty simple. Trans products are generally favored over cis products because of what we call steric hindrance. And here's a picture of that. Right, a trans product, the hydrogens are kind of further away from each other, so it's easier to make. It's a more stable compound compared to a cis product where the hydrogens are all kind of getting up in each other's business there. If you want to see a 3D look at it, here it is in 3D, and you can see it on mol view, where this one, the hydrogens are kind of close to each other and kind of getting in each other's way, and this one, it's more straight and more out. And maybe I can do that opaque thing, and it really shows it off a lot better. There you go. See how this one, there's like, the hydrogen bubbles are getting up right next to each other. This one, they're more out of each other's way. You can also see how much electron density there is around that double bond. That's why things like to attack double bonds and get added across it and things like that. So that's elimination reactions, and that's why trans is favored over cis because of this thing called steric hindrance. That is elimination reactions, and that's the end. So just as a review of what we did here, we talked about alkenes and introduced priority. We talked about cis versus trans, which is this is cis and this is trans. And the double bond won't twist, and that's why this stays cis and this stays trans, because the double bond can't twist. We talked about addition reactions, where we're actually breaking up the double bond and installing something across it where these two used to be, one on each carbon, and Markovnikov's rule, which helps us predict it. We talked about aromatic compounds, naming things as either a benzene as the central molecule or a phenyl group as a side chain. We talked about alcohol naming, where it ends in "all" and it takes priority from everything else. We covered, this weird naming thing that we did. And we talked about elimination reactions in Zaitsev's rule, where we take away, say, an alkyl halide, or we take away, say, an OH group, and it has to pull a hydrogen from something else. One thing to watch out for, I'll do this on the whiteboard very quickly, is if you look up there, we have to eliminate from 2 carbons to create a double bond. You have to watch out for that. So, like, for example, let's say I had something like this molecule, which is perfectly fine, and I wanted to eliminate it, right? The elimination reaction just calls for a strong sulfuric acid or phosphoric acid, H2SO4. Which product would be favored, right? And you go, oh, okay, well, you know what? The hydrogens are going to tend to stick together. So there's 2 hydrogens here, and there's no hydrogens here. So I predict that the double bond is going to be formed there. But remember that elimination, we're going to make water, H2O. Where's the other hydrogen going to come from? There's no hydrogens here. This is already making 4 bonds. This is impossible. You can't make this double bond. You can't install this double bond. Because if you did, right, if you did install that double bond there, then this carbon is making 5 bonds, and that's not a good carbon. So that means that in this case, there is only one product. The product has to be here. We're going to pull this OH away, pull that away, pull one of these hydrogens away, and install the double bond there. And so our only product can be this guy, plus H2O as a byproduct. So yeah, do be careful with that. Remember that we're pulling it away from both carbons in order to make space for the double bond. That's it. That's a bunch of reactions all at once. But now you've learned about elimination reactions, substitution reactions, and addition reactions, and some rules that help us predict them. So yeah, that's it. Thanks a lot, and I will see you in class.